we get is the well-known Rosenbluth formula. This will again be we discussed the Mott scattering. It's nothing but Rutherford scattering with relativistic corrections. That is what Mott scattering is. And then this object will be theta. Obviously theta is the scattering angle as we defined for that particular process. It is the same thing, angle between the incident and the. Now this GE is called the electric form factor of a neutrino Gm. Well, let us go back to this case. That what happens in the low momentum limit? This form factor reduces to 1. But this is because we factored out the charge distribution ZE into this one, this point-like scattering. That contained the factor ZE. But if we didn't do it, if we parameterize the form factor in such a way that ZE is included in the definition of the form factor, then at the low momentum limit, form factor will reduce to ZE, the charge of the total charge of the charge distribution. That is what I mean by it behaves like a point-like particle with charge Z. So therefore, it is expected that GE at rho q square will reduce to q by E, where q is the charge of the nucleon in units of the fundamental unit of electric charge. And what is mu n? So mu n is the nuclear magnetron. You know that for the electron the magnetic moment is expressed in units of Bohr magnetron. In the case of nuclear magnetron, this will be E over 2 mass of the nucleon in natural units. So therefore this ratio simply measures the departure from point-like behavior in the sense that, recall the magnetic moment of the electron, it was some g times over magnetron, and in the case of electron it is calculable. As I told you, those of you who have done relativistic quantum mechanics, who have done Dirac equation, you know that it follows from Dirac's theory that for a point-like particle, E should be 2. Now in the case of this, electron is a point-like particle, nucleons are not, therefore G in that sense is not calculable from a fundamental theory. Again, one can make models. In quark model, for example, you can calculate the magnetic moment of the nucleon, but that's a different story. So this is like something which parameterizes also the departure from the point-like behavior. If this was a point-like, then this G magnetic would go to 2. What is the G factor of a point-like spin half particle? In this case, it turns out that G electric proton is 1. Just like that case, because the charge of the proton is here and that is 1 anyway. And G of neutron E, 0 means when Q square goes to 0, this is 0. Neutron has no electric charge. And this is not true at all. This is 2.79. So this shows significant departure from the point-like behavior, and in this case this is totally bizarre. It turns out that the magnetic of the neutron is minus. What does it mean? It means that for neutron the magnetic moment and the spin are antiparallel. Now again, as I told you that some of these things can be calculated in the quark model, but that is not the subject of the discussion today. So I stop here this particular discussion, but unless you take a model, it is impossible to calculate these quantities. Unlike the form factor in the simple case, it is impossible to calculate these quantities from fundamental quantum field theory. You just cannot say that I will apply quantum field theory step by step. And so now, first of all, let me tell you what deep inelastic scattering is. Now we have an electron. These are all 4 momenta, and then a photon is exchanged. This carries Q. I should put something. Here somehow I decided to put K for the incident and K prime for the scattered. And then the physically means, what algebra, what X stands for in algebra, that is something unknown. And here what is unknown? Unknown is that this X can represent any experimentally. What it means is quite clear, that is, we will not look into what comes out with the electron. It can be 3 proton, 3 proton is a Pyrotic barrier number. It can be 1 proton and 1 pion, it can be 1 proton and 5 pion. Depending on the energy, all these things are possible. And we won't care what comes out with the electron. We will only measure the behavior of the electron. Okay, what is the number of electrons coming out of a particular solid angle? That is d sigma d omega for the electron. Scattering angle of the electron. What is the change momentum of the electron? So this is what I mean by that X is anything. Alright. Now comes the question that obviously I have to parameterize this by something which is similar to the form factors. But it cannot exactly be the form factor because I don't know what is this here. Alright. So what we do is the following. So let me go back to a point like particle. I told you that for a point like particle this is known, and if you know a little bit of quantum field theory, you will know that this interaction for a point like electron can be written as that this u is the wave function of the initial electron, u bar is the wave function of the final electron. This is what we get from Dirac theory. Gamma mu is one of the Dirac matrices, and mu is the wave function for the photon. The only difference is these are not wave functions, they are quantum fields, but for simple understanding this is okay. But let me symbolically write that this is J mu times mu, and comparing this I know that J mu is scattering, this momentum can change. So therefore, the main point I am trying to make here is that for an interaction when a particle interacts with an electron, we can say that the particle, or even better, the force carrier particle is coupling to the electric current of the electron. The main point is current is known for a write as E times J mu, this time J mu of proton. Please put a E here. It is better to remind you that this is the current of an electron, which is a pointless particle. So this J mu is not the same as that of a point-like particle. And typically for the proton, I would like to write this J mu as now let me explain as much as I can. This means that electrons or protons are both spin half particle. Therefore, they in some sense obey Dirac equation. Although the proton is not point-like. In other words, if you take the free Dirac equation, they are exactly the same as that for the electron and the proton. When you consider interaction, it is different. So these are the wave functions of the initial and the final proton.
Sir, what is this? J mu p is the current for the proton.
Right.
And what is E J mu p?
Sorry.
Right.
So formally they are the same, but the trouble is I don't know J mu p. Now this is related to the spin of the proton, and by spin I can also think of magnetic moment, because the magnetic moment of the proton is due to its spin. This sigma mu nu is basically related to the spin of the proton. This q mu is the moment of transfer, and these two are unknown functions. And this is also unknown functions. And these are what we call form factors. Now you see, this formula is not a God-given formula. Let us look into the Feynman diagram. I know the electron current exactly. So if I parameterize, oh I'm sorry, I have erased that diagram. So let me draw it again. This is the elastic, not deep inelastic. Elastic electron proton scattering. So this I know from quantum field theory. No problem. In this case, the trouble is I don't know this current. Okay? I don't know what the proton current is. But if I parameterize the proton current in this